Hi, this is Dane Quinn, and I'm at the University of Akron. Today I'd like to do an example using Lagrangian equations for modeling multi-degree of freedom systems, and then I'll actually determine natural frequencies and mode shapes and talk a little bit about the response of the system. So here's what I'd like to look at. We have a bar, length L, that's pinned at one end, and then a second spring is located halfway down the other end. So this spring is a distance L over 4 from the mass center, and this spring is a distance L over 2 from the mass center. So each spring is equal, and I would like to find the equations of motion and then solve again for the natural frequencies and mode shapes of the system. So as always, we begin by thinking about the problem at hand. So here, this is a 2-degree of freedom system. We need 2 coordinates, and we'll actually define a number of different coordinates, but in particular we need to know where the bar is, right? So we could define one coordinate that describes sort of the vertical position of the mass center, and then a second coordinate might describe the rotation of the bar about that point. So let's look at the forces that act on this bar. So we'll represent the bar here, and then in this case I actually want to include the gravitational load. So that'll be weight W acting at the mass center. We'll have a force, say F1, acting from the left spring, and likewise we have a force F2 acting on the right spring. We now want to look at the forces that act on the system. Both the spring and the gravitational forces are conservative. So they will be included in the potential energy. And there are no other forces that act on the system. Right? There's no damping. There are, in this case, actually no constraint forces. So the system is conservative. Which means that everything is accounted for in the kinetic and the potential energies. And in particular, the generalized forces are by definition 0, because again, there are no non-conservative effects in this problem. So the first thing we do is coordinates, right? We want to identify the way that we're going to describe the configuration and the forces that act on the system. So as I mentioned, it's a 2-degree of freedom system. We'll start off and define directions I and J. We'll look at the linearized motion for this problem. So we'll assume that the angles are small, and in particular that implies that sine of theta is approximately theta, and cosine of theta is approximately 1. So now, going back, let's identify the forces that we need. Well, we had said that we want to define the displacement of the mass center. Right? So if G here is the mass center, the displacement in the vertical direction we'll define as x, and then the rotation of the bar we can define as theta. Now in addition we have these 2 forces. The force on the left depends on the stretch in the spring, right? So we'll define that as y1, and the force on the right depends on the stretch in the right spring, so that'll be y2. Now as a 2-degree of freedom system and 4 coordinates, we have 2 constraints. So in particular, we often define constraints in terms of velocities, right? So let's try to relate the velocity on the left and the velocity on the right to the velocities of x and theta. So in particular, let's start off with theta, or y2. So y2 dot, so again that's the velocity on the right, is going to be the velocity of the center, right? So that's x dot, plus the relative velocity between the center and the end. So if this bar rotates with angle theta and angular velocity theta dot, then this relative velocity is L over 2 theta dot. And of course, we could integrate this and relate the coordinates themselves directly. So y2 is equal to x plus L over 2 theta. Doing the same for the left, we see that y1 dot is again the velocity of the center, and now this relative velocity is in the minus j direction, so that would be minus L over 4 theta dot. So once again, relating the coordinates directly, y1 is x minus, this should be a 4, L over 4 theta. So now let's turn to the kinetic energy. Well, this bar is moving in a general fashion. So the kinetic energy we'll write as 1/2 mass times the speed of the mass center, so that's Vg dot Vg, plus 1/2 times the moment of inertia of the bar about the mass center, times theta dot squared. So here, the velocity of the mass center is x dot in the j direction. So this term, due to the translation of the bar, is x dot squared, and then the moment of inertia of the bar about the mass center is ml squared over 12 times theta dot squared. So this is the kinetic energy of the bar, and it's naturally written in terms of the position of the mass center and the rotation about the mass center. Now, if we turn to the potential energy, we see that V, the total potential energy, is V due to the spring on the left, plus V due to the spring on the right, plus, finally, V due to gravity. So here, spring on the left, 1/2 k. The stretch is defined as y1. For the spring on the right, the stretch was defined as y2. And for the force due to gravity, the height above our datum point is simply x. So now I've got the total kinetic and the total potential energies, which means that I can form the Lagrangian as the difference, T minus V. So that's going to be m over 2 x dot squared. I'll just rewrite the kinetic energy that I've already found, and then I'll subtract from that the potential energy, again, that I've already found. So there's y2 squared and mgx. So now I have the Lagrangian written in terms of x, theta, y1, y2. And we also need these coordinate relationships. So I need to choose two of these, right? In particular, let's choose to do this in terms of y1 and y2, right? So really, I need to express these constraint relations and solve for x and theta in terms of y1 and y2. So I've actually done that, and what we end up finding is that theta here is y2 minus y1 divided by 3L over 4, and x is 2y1 plus y2 divided by 3. Right, so again, I've already solved these two constraint equations that are naturally given in terms of y1 and y2 in terms of x and theta. So here, I can take this relationship for theta and introduce it here, this relationship for x, introduce it here and here, and we end up finding Lagrangian written in terms of simply y1 and y2. Now, again, I've done a little bit of algebra, and I've made those substitutions in here, and this is the final result. So this is the kinetic energy, written in terms of y1 and y2. This is the potential energy, again written in terms of y1 and y2. So now we want to apply Lagrange's equations. Right, so again, here they are in general. We'll take our first generalized coordinate to be y1. Our second generalized coordinate will be y2. So let's go ahead and calculate the partial derivatives that we'll need. Right, so the partial of L with respect to, we'll do y1 dot first, is, well, 2m over 9 times 2 y1 dot plus y2 dot. So that's the derivative of this term with respect to y1. And then minus, in this case, 4m over 27 times y2 dot minus y1 dot. And likewise, partial of L with respect to y2 dot is m over 9 2 y1 dot plus y2 dot plus then 4m over 27. Again, this is the derivative with respect to, well, the derivative of the potential of the Lagrangian here with respect to y1 dot and y2 dot. And so, you know, if you're having trouble following, maybe pause the video, work these partial derivatives out for yourself. And then the partial of the Lagrangian with respect to y1, well, that's just from over here, and I get k times y1 plus now 2mg divided by 3. Doing the same for y2, I get ky2 plus mg over 3. So finally, we can apply Lagrange's equations and write down the equations of motion. Right, so this first equation becomes, well, I'm just going to go ahead and write them out. Right, I've done this sort of offline, a little bit of algebra, right, but we find this is 16m divided by 27 times y1 double dot. Right, so basically that's this term, which is 4m over 9, and then minus minus, so plus 4m over 27. And then we get a mixed term, 2m over 27, y2 double dot. The potential term gives us a plus y1, and actually the gravitational load, I'll move to the other side, as minus 2mg over 3. For the second equation, I get 2m over 27, y1 double dot, and then 7m over 27, y2 double dot, ky2 minus mg over 3. So these are the equations of motion for this system, right? And these are the equations that I want to solve. So in order to solve this, we need to solve a related eigenvalue problem. And part of that is identifying the mass matrix. So writing this in matrix form, we get 16m over 27 and 2m over 27. Those are the y1 double dot terms. 2m over 27 and 7m over 27. y1 double dot, y2 double dot. So these are the mass times acceleration terms. There's no damping because it's a conservative system. And the stiffness matrix is symmetric. And coordinates again are y1, y2. And then we have a forcing term, minus 2mg over 3 minus mg over 3. So here, this is the mass matrix, this is the stiffness matrix, and then this is the forcing term. Meanwhile, this is the vector of states, this is the acceleration vector. So we have our matrix equation, mx double dot kx equals forcing. So now we want to look at the response of the system. Well, it's determined in terms of the mode shapes and natural frequencies, omega, which come from our eigenvalue problem. We talked about this in a previous lecture. Right, so K, the stiffness matrix, times U, the mode shapes, equals lambda mu, and we need to solve this for lambda and u. Well, that amounts to taking the determinant of K minus lambda m and setting it equal to 0, with m equal to this matrix, which was found on the previous slide, and then K also found from the equations of motion. So before I actually do this, I want to talk about a simple transformation that we can do. Notice that both the mass and the stiffness matrix have a parameter in them, right? M parameterizes the mass matrix, and remember, m was the mass of the bar. K is the mass of the spring, or the stiffness of the springs, and again, that parameterizes the stiffness matrix. Well, in general, we would have to solve the eigenvalue problem in terms of these parameters, but we can actually apply a simple transformation that will sort of scale away the mass and the stiffness values m and k in this case. So, to see how that works, I want to define the mass matrix, again, as 16m over 27, 2m over 27. Again, it's symmetric, right, because it has to be with Lagrange's equations. It's 7m over 27. Notice that I can actually factor out a constant from this, and that constant will include the unknown mass m. In this case, I'll factor out an m over 27. 27 is also common to all of these terms, and I end up with 16, 2, 2, and 7 as my mass matrix. Right, so I'm going to define that as m star times m hat, where m star is this constant that we factored out, m over 27. And then m hat is the matrix that remains. Notice that m hat is purely numerical. So we'll do the same thing for the stiffness matrix. K is, again in this case, 0, 0, K. So I'll factor out this constant K, which leaves the identity matrix. And we'll define this as K star times K hat. Now, depending on the problem at hand, K hat may not be as simple as the identity matrix, but it does have this constant value K factored out. Right? So again, K star is defined as K. So how does this help simplify our problem? So here we have a simple transformation, and in particular we've identified a parameter m star and a parameter k star so that the resulting matrices are purely numerical. M hat is just this numerical matrix here. K hat is this numerical matrix given here. And they don't have any parameters in them. All the parameters are inside these k star values. So how does that affect the eigenvalue problem? Well, the eigenvalue problem was Ku equals lambda m times u. And what we really want is to solve the determinant of k minus lambda m equals 0. So the way that I'll approach this is to make this substitution. And so here, k star k hat u equals lambda m star m hat times u. So all I've done is just substituted in these new representations for the mass and stiffness. But when I do that, I would like to divide through everything by k star. And then I can identify a new parameter, beta, which is lambda m star divided by k star. And when I do that, my eigenvalue problem becomes k hat u equals beta m hat u, because lambda m over k is simply beta. So now this is the problem I'd like to solve in terms of these scaled matrices. And that's just another eigenvalue problem. I want to find the values of beta and u, the mode shapes, or the eigenvectors, that solve this problem. Right? So essentially, we're now solving the determinant of k minus beta m is equal to 0. Except, this is great because everything here is numerical. Right? K hat is a numerical matrix, m hat is a numerical matrix, and all the parameters of the problem, namely m and k, have been sort of sucked into this beta. Now once I solve this, I have to go back and solve the original problem. Well, that's fine. All I have to do is, now given beta, recognize that lambda is beta times k over m. And so the solution to this problem is related to the solution of this problem through this transformation. Again, the original problem has parameters in it. This has no parameters in it. And the other interesting thing here is the mode shapes for the two problems, the two eigenvalue problems, the original problem and the scale problem, remain the same. So it's only the eigenvalues that I need to scale to go between these two problems. So again, this is just a simple transformation that sometimes can make our analysis easier, right? Because we don't have to deal with parameters. All those parameters are located kind of inside of beta. And then we have to bring them back out again to find the actual original frequencies, or the eigenvectors, or eigenvalues, sorry. Right, so let's look at the problem that we actually are dealing with. We want to find the determinant of k minus lambda m equals 0. And so in terms of our scaled values, that's the determinant of k hat minus beta m hat equals 0. Right, so really what we're talking about is solving the following problem. The determinant of k minus beta m. Right, so that's 1 minus, well, in this case, 16 times beta minus 2 beta, 1 minus 7 beta, and minus 2 beta there, equals 0. Right, so this becomes our characteristic equation. Right, so when we write this out, it's 1 minus 16 beta times 1 minus 7 beta minus 4 beta squared. And expanding that, I get 108 beta squared minus 23 beta plus 1 equals 0. So this becomes our characteristic equation for this problem. And we can solve this, right? We can find beta 1 and 2, so the two values of beta end up as 23 divided by 216. Obviously I did this kind of ahead of time, but it's easy enough to verify. So there it is. These are the eigenvalues. And numerically, we end up with 0.0609 as the solution with the negative sign. and 0.1521 as the solution with the positive sign here. So now I need to go back and find the Eigen Vectors. Right, so that eigenvector problem looks like K times U. So here ui1 and ui2 are the elements of the eigenvector, equals eigenvalue times m hat 16227, and again the eigenvectors ui1 and ui2. Right, so essentially we need to solve one of these rows for u2 in terms of u1. Right, so looking at the first row, we have ui1 equals beta times 16 ui1 and 2 ui2. So now ui2 is 1 minus 16 beta divided by 2 beta times ui1, where ui1 is arbitrary. Right, so in particular, if we choose ui1 to be equal to 1, then we can solve for ui2. Right, so doing so and finding the final solution, right, we see that lambda, these are the eigenvalues, are beta times k star over m star is on the previous slide. Right, so for this problem that ends up being 27 beta over times k divided by m. Right, so we have two solutions. Lambda 1 is 1.644 times k over m. Right, so omega 1 is the square root of lambda 1, which ends up being 1.282 square root of k over m. And using this value of beta, right, from here into this expression for the mode shapes, we see that the first mode is 1 and then 0.210. Right, so that's the first mode shape. Likewise, for the second eigenvalue, lambda 2 ends up being 4.106. Again, did this ahead of time. Omega 2, which is the square root of lambda 2, is 2.026 square root of k over m. And then finally, u2, the second eigenvector, is 1 and minus 4.713. Right, so these are all the numerical values that we get from this analysis. So really, that's the problem, right? We have gone through, we've modeled, and we have solved the eigenvalue problem. In particular, we had this scaled characteristic equation, which we solve for beta, and then we recover the original eigenvalues. We use those then to find the mode shapes, right? But if you're looking closely, we're only on slide 6 of 7. So let's look and see what these modes sort of imply physically. Right, so the first mode, this is the frequency. But if I look at the mode shape, we have 1.210. Now remember, these mode shapes corresponded to coordinate y1 and coordinate y2. So mode shapes are arbitrary in length. All they do really is provide a relative displacement of one coordinate versus another. So here we have a relative displacement between two coordinates. So in particular, this was y1. Right, so let's say that this displacement is some constant, c. What that implies is that the displacement of y2 is 0.21 times whatever the displacement of y1 was. And the mode shape here looks kind of like this. The bar rocks back and forth as the point on the left moves up, right? The point on the right moves up as well. As it moves down, the right moves down, right? So this actually we would say is an in-phase mode, right? So both coordinates are moving together. Now, mode 2 is an out-of-phase mode. So how do we see that? Well, here, if the displacement on the left is some value, c, and in this case, c would be a negative number, but what's really important is the relative size and the relative sign. If this displacement is c, then this displacement is minus 4.713 times c, much larger. And in particular, this is an out-of-phase mode, because if the displacement on the left is negative, the displacement on the right is positive. Now, the in-phase modes, the sign of the displacements was identical. Out-of-phase modes, the sign of the displacements is negative, or opposite. So here, if this moves down, this moves up. If it were to move up, this point would move down. So we have these two characteristic mode shapes for the response of the system. And in general, the overall solution is a combination of these two kinds of behaviors. One in phase, which happens at a lower frequency, and one out of phase, which happens at a higher frequency, namely mode 1 and mode 2. Right, so this is a second example that we've seen using and solving for multi-degree of freedom systems, modeling with Lagrange's equations. So, I will talk to you again soon. Thank you very much. Bye. And then we have forces that act from the springs, right? So we'll say F1, and also we have dogs, apparently, that are barking because cars are driving by. Because they've never seen a car. Oh, there's a dog. Well, they've definitely never seen another dog before. You guys, this is why it takes me forever to do this. Don't come over here and lick my hand.